In this section, we'll look at logarithmic and exponential equations and how to solve them. But before we do sort of the grand generality, let's just remember what it means for something to solve an equation. So x solves an equation if when you plug it in, everything works. Okay, so if when you plug in x, the thing which you thought was an equation is actually true. Okay, so let's just take sort of a stupid algebra example. 3 is a solution of x plus 2 equals 5 because 3 plus 2 equals 5, and so 5 equals 5. That's true, so this thing is a solution. Okay, now that was a really cheesy example. What we're more interested in now is what about if the equation that we have involves exponentials or logarithms. So let's take, for example, this one, log base 6 of x plus 5 equals 4. Okay, now there's really two questions that we could ask here. The first is, this is an algebraic equation, maybe there's some way to solve it. And there is, and we'll talk about that. But if we had a number which we thought was a solution to this equation, how would we test whether or not it actually was? Well, like up here, we'd plug it in and we'd see if what we got made sense. Okay, so let's just take a couple of sort of random numbers here. Let's take x equals 19. So if I plug this in, then I get log base 6 of 24, because that's 19 plus 5, and I want to know, does this equal 4? Well, I can tell you immediately that it doesn't equal 4, and we can do so without a calculator. And that's really the important thing here, that while it's true that I could compute the log base 6 of 24 and figure out what that equals, I don't have to bust out a calculator in order to answer this question. So let's remember what it means for this to be the case. So this is true, log base 6 of 24 equals 4, if and only if 6 to the 4 equals 24. So notice that I've used the properties of logs and exponents. The base is here, the base is here, and then I've got the old thing being logarithmed and the answer on this side, and then the answer to the logarithm becomes the exponent here. And so this is only going to work if 6 to the 4th equals 24. Now I know that's definitely not going to be the case because 6 to the 4th is the same as 36 squared, and there is no way that that equals 24. This is going to be way bigger. So I didn't actually have to compute what the value of log base 6 of 24 is. I might want to in some situations, but here all I wanted to know is that or is it not equal to 4? And by the argument over here, it's clearly way different than 4. And that's all we were interested in. Okay, now if you've got one that works, so let's just take 1291. This actually does work. So this does work because if I take 6 to the 4th, it equals 1296, and that happens to be exactly 1291 plus the 5 that's over here. So I've got 1291 plus 5, so the log base 6 of that equals 4 because 6 to the 4th does in fact equal 1291 plus 5, or 1296. And in this case, it's maybe a little bit of a cheap shot because, of course, I did cheat to realize that 6 to the fourth is 1296. That's not something I'm going to do in my head. Um, yeah, but this is a lot easier of a computation. I mean, if I had to, I could have computed 6 to the fourth by hand by just doing 36 by 36, whereas there's absolutely no way that you're going to be doing this computation by hand. Okay, so not too difficult. So in the next sort of segment, we'll look at actually solving an equation that's sort of like this form, rather than just testing whether or not something is a solution to it. Okay, so let's look at a simple exponential equation. Um, that doesn't actually require the use of logarithms, although you certainly could to solve it. So the sort of most simple exponential equations we could have would be something like this. 2 to the x equals 32. And you might be able to solve this in your head, actually, if you know the powers of 2. So for example, I know that 2 to the first is 2. 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, and 2 to the fifth is 32. So 2 to the x equaling 32 means that 2 to the x has to equal 2 to the fifth, because 32 is 2 to the fifth. And then here we are going to use sort of a property of exponentials, namely, and I'll write this in a different color, we had a to the x equals a to the y implies x equals y. So the exponential functions are one-to-one, and so if we have a situation like this, we can immediately conclude that x must equal 5. So the way that we did this was to recognize that it was possible in a very easy way to write 32 as a power of 2. Now, if that weren't easy to do in our head, then we have to use logarithms. And so let me just show you how we would do that here. So if I've got 2 to the x equals 32, what I can do is take the logarithm of both sides. And it's up to me what base I use for this. There's two arguments that you could make here. One would be to use base 2 because the problem had something to do with base 2. The other would be to use base 10 or base e because that's what's on a calculator. So if I did it with base 2 logarithms, this is what I would have. The log base 2 of the left-hand side must equal the log base 2 of the right. And then the log base 2 of 2 to something is just x. And then this side, this is actually 5 because of what we just observed over there. And so we would get exactly our answer. If we wrote it with natural logs, for example, we'd have this. And so x natural log of 2 would be natural log of 32, and x would be natural log of 32 divided by natural log of 2. Now, it is not at all obvious that this, in fact, equals 5. Although we can sort of rewrite it here to see that this is, in fact, 5, because 32, we said, was 2 to the fifth. And so this is what we have. The 5 pops out, and then the logs 2 cancel, and we get 5. So in the situation where you can easily express one thing here as a power of the other, then you can pretty much solve all of this by hand. And even if you do use logarithms, which is how we'll do in class, you'll end up getting the same answer, although it may initially look quite different, even though it actually is the same thing. But in a lot of situations, in real-world ones, it doesn't work out to be a clean power like this, and you have to bust out a calculator to at least get a numeric approximation. And so that's what you would do in one of these two solutions. You'd first write the answer as something like this. That's the exact answer. And then if you wanted to get a decimal approximation, then you certainly could. And just by way of reminder, if you want to see how to do the decimal computations with Wolfram Alpha, look back at the last video for an example of how to do that.